Hi students. In this lecture, I am going to discuss magnetic field. Let us see first list of concepts. First one, force on a charged particle. Second, force on a current carrying conductor. And the last one, torque on a current carrying loop. Let us see first one. So magnetic force acting on a charged particle, F bar equal to Q into V bar cross B bar. So this result is based on observations. See, from this, what we can conclude. If a charge is zero, then there is no magnetic force. That means on neutral particles, magnetic field cannot exert force. For example, neutrons. Okay. Next, coming to here, V bar. It is velocity of the charged particle. So this indicates that magnetic field cannot exert magnetic force on stationary charges. Getting the point. If velocity is zero, there is no magnetic force. That means magnetic field exert a force only on charged particles. Right? Next, you can see V bar cross B bar. Since it is now cross product, force is always normal to the plane containing V bar and B bar. This is what we have learned while learning cross product of two vectors. Right? And direction is given by right hand rule. That is, keeping our fingers of right hand on first vector, curling fingers towards second vector. That gives direction of force, right? Now let us see the possibilities here. If angle between V bar and B bar, so here B bar stands for magnetic field strength. So between the field vector and velocity vector, if angle is zero, I'm taking theta as the angle between those two vectors. Angle is 0 or 180. Then see what happens. Angle 0 or 180. This is V into B into sine of the angle. Sine 0, 0. Sine 180, 0. That means no force acts on the particle, right? That means if velocity of the particle is along the field direction or opposite to field direction, then magnetic force is 0. That means here net force equal to 0 because we are taking here only presence of magnetic field, no gravitational field, no electric field, and no other forces are present. Only magnetic force. So since it is 0, net force equal to 0. So net force 0 means acceleration equal to 0 because net force equal to mass into acceleration. So acceleration is net force by mass. Acceleration 0 means velocity is a constant. Velocity is constant. So velocity constant means same speed, same direction. That implies path is straight line. So we are knowing that velocity constant means it is known as uniform motion. Uniform motion path will be straight line. Okay. Next, see the next possibility. If theta equal to if theta equal to 90. If theta equal to 90, modulus of the force is maximum, right? Q V B sine 90. So modulus of the force is maximum. And you can see this force is always normal to velocity. That means speed of the particle does not change. It is only change of direction, right? And if you remember, while discussing uniform circular motion, if you see that uniform circular motion, net force, which is nothing but centripetal force, that is always normal to velocity vector, right? Now you can say same thing here. F bar is always normal to velocity vector. Okay, between those two, always angle is 90. That means theta is 90. It will be uniform circular motion. It is uniform circular motion. Okay. So when angle is 90, path will be circle. It is uniform circular motion because speed is constant. And whenever path is a circle, first we have to focus who is providing centripetal force. So here the only force is magnetic force. Therefore, magnetic force provides centripetal force. So I'm writing here centripetal force equal to mass into centripetal acceleration. Now magnetic force is QVB because angle is 90. That is equal to M. Centripetal acceleration is V square by R. From this we can write radius of that circle is equal to MV upon BQ. Right? Or we can write radius in the place of momentum MV. MV stands for momentum. So in the place of momentum, so we are knowing that kinetic energy equal to P square by 2M, right? So in the place of P, we can write, in the place of P, we can write root of 2mk, right? Therefore, radius equal to, it is in the place of mv, root 2mk upon b. Okay. So radius of the circle is mv by b cube, or in the place of mv, root of 2mk upon b cube, right? Now we can focus here. What is time taken to complete one revolution? Time taken to complete one revolution. And that is given by distance traveled. It is not displacement. It is distance traveled 2 pi r upon speed. It is not velocity, speed. So now we can substitute in the place of mv by bq, mv by bq. Then see what we get. 2 pi by v. This is mv by bq. So v gets cancelled. It is now 2 pi into m by bq. Okay. So time taken to complete one revolution, which is known as time period of revolution, right? Suppose question is like, what is the time taken to complete half revolution? Half revolution means here we have take distance traveled is pi r by v, right? Or I can say from here, half of the time period of revolution. That means in the place of 2 pi, we have take pi to complete a half revolution. Okay. Or if the ask like time taken to cover an angle theta, how much? Then we can write it is equal to, in the place of 2 pi, writing theta into m by v cube. Okay. time taken to cover this angle theta, how much means in the place of 2 pi writing theta into m by bq, right? Next, if we take reciprocal of time period, that gives a frequency which is equal to bq upon 2 pi m, right? That is the frequency. And if you see carefully, time period of revolution is not depending on speed. Generally having a misconcept that if a speed is more, it covers in less time, right? But we have to remember that when speed is more, radius is also more. That's why even though speed is more, time period of revolution remains the same. It is independent of speed. More speed, more radius, right? Okay. Next. Now here we have to focus one more important thing, direction. It is V bar cross B bar. Okay. And we are knowing that in case of a cross product, direction is given by right hand thumb rule. That means first we have to choose our right hand, placing the fingers on first vector, that is V bar. Curl fingers towards second vector. That gives direction of cross product. Okay. Otherwise, without using hand, we can use now vectors. Let us see. So we are taking our left hand is indicating east. Imagine you are sitting or standing by stretching your hands. So right hand will be towards east. Right hand, left hand towards west. Means we are taking right hand. It is east, left hand towards west. In front of us. In front of us, that is north. Behind us, it is south. Okay. And we are taking east as I cap, west minus I cap, north j cap, south minus j cap. Okay. So we are using now this notation to find out direction of force. Let me take one example here to get more clarity. For example, take a positive charge. Charge is a positive. Velocity is now vertically down. So here we are taking east I cap, west minus I cap, north j cap, south is minus j cap. Vertically up k cap, vertically down minus k cap. Now velocity, take it as v naught into minus k cap. Means it has velocity vertically down. Okay. Suppose a field is, it is a b naught into j cap. See meaning of this? J cap field is now towards north. That means it is from south to north, right? So velocity vector is now direction minus k cap. So now we have to focus when this a particle enters into magnetic field. What is direction of force? Because direction of force keep on changes, right? So we're asking that just after entering into the magnetic field, what is it? It is just after entering into the magnetic field, what is direction of force? F bar direction. Then take now this one, Q into V bar cross B bar. First thing, Q, it is positive. Okay. So we should be very careful here because there is a possibility of making mistakes. Charge is a positive. Therefore, direction of F bar is direction of V bar cross B bar. If charge is a negative, direction of F bar is opposite to the direction of V bar cross B bar. Okay, that's my first cross check. Charge is positive. Okay, next V bar cross B bar. V bar minus K cap. Direction is minus K cap cross B bar. B bar is now J cap. Right? Now cross check once minus K cap cross J cap. If you see how we remember this, I cap, J cap, K cap, I cross J, K cap, J cap cross K cap, that is I cap, right? It is now reverse. K cap cross J cap, K cap cross J cap is minus I cap, but having here minus, it is I cap. That means just after entering into the magnetic field, force will be towards east. So like this, by using vector notation, we can get direction of force. Okay. Next, coming to here, when angle is 90, path is now circular. So here we have to focus what is the plane of the circle. Okay, which is very important while solving problems. Let us see now how to decide that. For example, we are taking a positive charge. So we are taking a positive charge, charge positive. Suppose velocity vector, it is along positive x-axis. And a magnetic field vector, it is along y-axis, j cap. Okay. So take the question is like projecting a positive charge from origin along a positive x-axis. Field is along positive y-axis. Okay. So now we want to know to which plane this circle is confined. Okay. So first of all, decide direction of force. Charge positive. Therefore, direction of force is direction of V bar cross B bar. Right? That means I cap cross J cap. I cap cross J cap. That is K cap. Right? Now see carefully here. I cap cross J cap means it is K cap. Let me take this is X axis and this is now Z axis. Okay. So for our convenience, we are taking this as, you can say this is a board plane. This board is now XZ plane. Okay. And why I have taken XZ plane means because here force is now along positive Z axis. So you can see here velocity. Velocity is now along positive X axis. Velocity. Right? But force is now along positive Z axis in this way. Right? Then see how the path will be. The path will be now, it deviates from x-axis, means it is now like this. Circle comes like this. Okay. So I will draw the circle separately here. So motion is confined to xz plane. Okay. And circle will be, So this is z axis, this is x axis. Circle is now starting from origin. So circle is now like this. Okay. It is anti-clockwise. This is x and this is z, right? So motion is a confined to x z plane. And here one more thing we have to observe carefully. Since a force is always normal to velocity vector, it is changing only direction of velocity, but not magnitude. That means its a kinetic energy is always the same. I am repeating. Since magnetic force is always normal to velocity vector, it changes only direction of velocity, but not magnitude. Okay, that means its kinetic energy is always constant. So if you take this is the only force acting, then this becomes now net force. And we have learned that work done by net force is equal to delta K. Now here delta K equal to 0. That means no work is done by magnetic force on the charged particle. Okay, that means speed is now constant. So when speed is a constant, you can see here motion confined to xz plane. So you're having here for velocity two components, x and z. So we can write at any instant bx square plus bz square should be equal to v naught square because speed is a constant. Okay. Next, you can see here for half of the time period of revolution, it's up to here for a half of the time period of revolution, it has velocity component. It has velocity component along positive z axis. See carefully, starting from origin till completing a half revolution, it has velocity component along positive z, right? Next, and if you observe till one fourth of revolution, its velocity component along x-axis is positive x-axis. After that, it is along negative x-axis, right? So we can expect some simple problems based on this theory. Okay, right. So here the final key point is that observe carefully direction of force. Basing on that, we decide to which plane circle is confined. If we know that, it becomes very easy to solve problems. Okay. So till now we have taken 0, 180 and 90. Now see the next possibility. Next possibility. If angle is not equal to 0, not equal to 90, not equal to 0, not equal to 90, and not equal to 180. Then what is the path followed by the particle? Let us focus now that. So third case, theta not equal to 0, 90 and 180. Okay. So let us take here. This is magnetic field vector. Now velocity vector makes angle theta with a field vector. This is V bar. Okay. So here what we are doing is for velocity vector, we are taking two components. One is along the field. Let us call it as V parallel, means parallel to B bar. Next one, it is V normal. That means normal to V bar. So take now two components. And we have learned that if velocity is a parallel to B bar, that is a first case, right? If velocity is a parallel to B bar, path will be straight line. Okay. Next, second case, if velocity is normal to B bar, path is circle. Now here it is a combination of straight line and circle. Okay. And that we are calling as a helical path. See carefully. So path is now helix. It is known as helix. It looks just like a spring which is stretched. Spring which is stretched. Okay. And for this helix, so just imagine one spring and slightly stretch it. The shape which we are going to get, that is helix. And for that spring, you can see what is radius, right? That radius is given by r equal to m. V perpendicular, okay? You just observe. If we have only normal component, what is radius? That is m v perpendicular upon v cube, right? That is now radius of that helix, okay? And next, you can see after every revolution, after completion of one revolution, the particle touches this field axis. I am repeating, after every revolution, the particle touches this field axis. So if you are taken now that V parallel into time period of revolution, that is known as a pitch of the helix. It is known as pitch of the helix. Okay. Let us see so far what we have discussed. See the theory points once here. Force on a charged particle given by F bar equal to Q into V bar cross V bar. Angle 0, 180. Velocity constant. It is uniform motion. And the path is straight line. Theta is 90. Path is circular. It is uniform circular motion. That means speed is a constant. Okay. Theta not equal to 0, not equal to 90, not equal to 180. Then path is helical. And pitch. It is magnitude of the displacement component along the field in one revolution. And finally, the most important point, work done by magnetic force on a charged particle is zero because force is always normal to velocity, no change in speed. Okay.